We'll get done with part 7 in case you're a slide counter, and we might get done with part 8. We shall see. So stoichiometric calculations are you have your reactants and your products, and basically you want to go from the mass of something to the mass of something else. But it's all about going through the moles, and we know we use molar mass to go through the moles. So you go from grams to moles using the molar mass of what you do know. Then you go from moles to moles using the ratio from the coefficient from the balance equation. Then you go from moles to grams using the other molar mass. It's a pattern. Well, that's stoichiometry. Well, limited supply stoichiometry takes it is kind of the yang to simple stoichiometry. So you have simple stoichiometry, limited supply stoichiometry, and they're related. In limited supply stoichiometry, you have to identify what you're going to run out of first. So what you're going to run out of first, reactants, so we're talking about reactants on the reactant side. Just say you have 2 reactants, and the one you're going to run out of first is in limited supply, and the other one is in excess. Now, if you're going to go ahead and take the 2 and put them together, say you have 2 reactants, if you're going to put them back together, have them react to form products, and you don't have anything at the end, we say that they are present in the stoichiometric ratio, whatever this says, that they're stoichiometrically just perfect. Means you run out of both of them. Okay. Now, if you have 3, does this make sense? We're going to do an example here. If you have 3 things that react, then how does this work? It seems like one you're going to run out of first, and that would be in limited supply, and the other 2 will be excess. It's possible that 2 of them are in limited supply. They're just the right same amounts, and then you have 1 excess. It's possible. See what that looks like. So we're making sandwiches here, and well, actually, before we do this, this was my my little different thing for today. I wonder if this will. Oh, and I don't know how this exit. See, I did I think it goes there. I put this together because this, I told you how chemical equations to me seem like recipes. So here's a recipe for some crazy cookies. I don't know what kind of cookies they are, but here are some standard ingredients in cookies. So we're going to need half a cup of sugar. What I have, I think I did have a quarter cup when I was in my office, but it went up to a half a cup of butter, 2 cups of flour. Will make us 4 dozen cookies. And we know that we can kind of scale those stoichiometric coefficients. So for instance, let's see how we do this. Change my pen color. Yeah, red works. So if I want to scale it up and say I wanted to make 8 dozen cookies, I could go through and I could take everything times 2. So that would be 2 cups, 1/2 times 2 is 1. So I need 1 whole cup of sugar, 1 whole cup of butter, and 4 cups of flour. That'll give me what, 8 dozen cookies, right? We kind of talked about that. That's the whole scaling up. We could scale down and that sort of thing. Well, let's just say you go to your cupboard and let's say, oh, this is not going to work. Yeah, I guess this will work. Let's say that you have, so this is what, I'm going to go ahead, we're going to use these terms here. I'm going to put need. The recipe says you need that. You go to your cupboard, let me change my pen color to purple. You go to your cupboard, and this is what you have in your cupboard. Let's say you go to your cupboard and you have, you do have 4 cups of flour, and let's say you have 6 cups of butter. Wow. And let's say you have 8 cups of sugar. So which one are you going to run out first if you're making cookies? Flour, exactly. So this is in limited supply, and these 2 are in excess. Exactly. So let's go back to this then. Maybe. Okay, so let's talk sandwiches. So in this example, the reactants are the bread and the ham, and the product is the sandwich. So kind of like what I said a minute ago, does this make sense that this 2 and this 1 is the need? That's what you need. That's the recipe. Now notice we've got some information about bread and ham down here. I'm going to go ahead and say have. This is what we have. So we have 20 slices. That wasn't supposed to be lined through there, but 20 slices of bread, and we have 7 slices of ham. So which one are we going to run out of first? We are going to run out of the ham first. I agree. So how many sandwiches can we make with the ham? 7. Very good. If we make 7 sandwiches, how much bread have we used? 14. If we use 14 slices of bread, how much bread do we have left over? 6. You guys have just totally answered everything we need to cover in this unit, or in this part. Okay? So you guys told me ham is in limited supply. Bread is in excess. You told me we could make 7 sandwiches. And you told me that we would have 4 slices of bread left over. That's it. Okay. So that's, you guys did that intuitively. Do you guys remember when we did factor label? I introduced you to factor label, and I was like, how many inches are in 2.5 feet? And you'd be like, 30, right? You just thought of it. But there's a technique to show you behind the scenes, and this is how that technique would work. So here we go. What we do is come up with what I call a have ratio. So I'm going to underline the word, need ratio. Oh, darn it. The need ratio. I'm going to show you my favorite way to come up with the limited reactant, which you guys told me is ham, right? Limited supply. This is how I come up with the limited reactant. There's 2 other ways at the end of this part I'm going to show you. All right, so you divide 2 by 1 and you get 2. So the ratio of bread to ham is 2 to 1. That's the have ratio. The need ratio will come from what we were given. So we were told what we have. Did I say need? Oh my gosh. The have ratio comes from what we were given. They said what you have in your cupboard. 20 slices of bread, 7 slices of ham. I have to get my calculator out and divide 20 and divide it by 7, and you'll get 2.86. What are the units? 2.86 slices of bread per slice of ham. In this method then, once you have the need ratio from the stoichiometric coefficient to balance equation and the have ratio from what you were given, you kind of compare the 2. So do you see where, let's see, I have. So have, with regard to bread, I have more bread than I need. Does that make sense? Now, well, I'm going to specify it's the thing in the numerator. I have more bread than I need. I have more bread than I need, and that's exactly what you guys told me. 20 was more than I need to make my 7 sandwiches. Okay, it's called you get the need ratio from the stoichiometric coefficient, you get a have ratio from what you were given in your cupboard. So you compare those 2 ratios, and based upon those ratios, okay, this is the sort of problem where you have to identify which reactant is in limited supply. That's all we're doing here. Which reactant is in limited supply? Honestly, this is one of those sort of problems where you're like, I got a 50-50 chance, right? There's only 2. But that doesn't work. And I'll try to kind of point out why it's so important to know which one you're going to run at first. So in other words, no matter how many sandwiches I want to make, you told me when we started this that most number of sandwiches I can make are 7. You got it. So let's kind of use stoichiometry to see what this would look like, factor label. So once I identify the thing that's there in limited supply, which is the ham, I can do my stoichiometric calculations. So I can take my 7 slices of ham, I can use this, I can come up with a ratio of slices of bread to slices of ham, Oh, sorry. How many sandwiches can I make? 1 sandwich for 1 slice of ham. 7. You guys told me that. 7 slices of ham. How much bread will I use? Well, I need to use 2 slices of bread for 1 slice of ham. You guys got all these, so you don't need to learn them down. Is that right? Okay. So that was the 14 you came up with. I mean, you guys can just eyeball this one. And again, that's great, but you can't eyeball all of them. How many's left over? We had 20 slices. We're going to use 14. Okay, and we're going to have 6 left over. So notice we took the available minus the used from stoichiometry's limited reactants and came up with what was remaining. Okay. So we could only kind of work our way through that series of questions after we, at the top, identified what's the limited reactant, and then everything else kind of falls into place. Put another way, if you incorrectly identify the limited reactant by just guessing, okay, all the other problems are going to be wrong. And honestly, if you get to working a problem like this on a test, if you come up with something at the bottom that doesn't make sense, it's probably because you misidentified the limited reactant. It happens to the best of us. I have a sheet for this one too. So, because I would put this up there and like, what does that mean? We're making we are making a handout, and our handout has 4 different elements, okay? And these elements we need, over here it is. So we need 1 title page, 1 sheet of instructions, 2 data sheets, and 4 pieces of graph paper. Okay, we want to make as many as possible. So here's what I came up with at my office, my desk. Oops. So I made like just kind of wrote down what we're looking at here. Okay. So the things in red are what we have. Oh, sorry, things in red are what we need. What do we need to make one handout? We need 1 title page, 1 instruction page, 2 for data, and 4 pieces of graph paper. What do we have? It's in purple there. So does this make sense? Well, first off, if I were going to, how many, just from the title page, how many handouts can we make? Just based upon 87 title pages. We can make what? How many? 87. And I bet you got that. Let's see if it's going to write for me. So you said, I have 87 and I need 1 per handout, so I can get 87 out of that. How many, just based upon the number of instruction papers we have, how many handouts can we make? 83. Cool. How about based upon 186 data pages, how many handouts can we make? 84. 84? I agree. And this one, I had to use my calculator. Yes, 82. Very good. I need 4 pieces of graph paper for every 1 handout. So if I take 382 divided by 4, yeah, I can make as many as 82 handouts. So which one's in limited supply?
Graph paper.
The graph paper, exactly. Does that make sense? So that the one that's in limited supply is going to drive how many handouts you can make, and then also how many title pages, instruction pages, and data pages that you're also going to use. So limited supply is really important. Actually, this method is one of the last pages, one of the last lecture slides in this part will say that this is one way to identify the limited reactant. Basically, you say, I take all my reactants, I max them out, I'm going to use them. How much product do I get? Well, whichever one gives me the least amount of product, that one's in limited supply. Okay, this is an alternative to the have ratio, or the need ratio, have ratio. All right. So, well, let's go back to something a little less silly. a little more like chemistry. This is called the Haber process. It's the making ammonia, which is the formula for ammonia is NH3. So we can take just like nitrogen, molecular nitrogen, because remember nitrogen is one of the diatomic elements. Okay, so it's always going to be molecular, two nitrogen atoms stuck together. Hydrogen's also diatomic. Okay, but in order to balance it, we need 1 mole of nitrogen for every 3 moles of hydrogen to make 2 moles of ammonia. Okay. So let's just say, have a little video to show you. Let's say on a small basis, a very small basis, we have 6 molecules of N2 and 12 molecules of H2, and they are going to connect up and make NH3. So this video will kind of show you what that looks like. We have known that. So we're gonna apply the need ratio to the have ratio. Here's another one. This is from your OpenStax textbook. This is kind of an interesting one because what is the ratio of, I guess I'll call it the need ratio. What's the need ratio of hydrogen to chlorine? How many moles of hydrogen to how many moles of chlorine do you need to react?
1 to 1.
1 to 1, yeah. So just off the top of your bat, if that's your need thing going on, what if you have 6 and 4? Which one's in limited supply? The one that's 4, the chlorine one. Yeah, it's exactly what you're going to see here. Okay. So, you know, there are just eyeball ways, sort of kind of looking at things. Sometimes when you work problems in science, there are often times you can take step back and look at it and say, does that make sense? So it's really important to be able to identify what's in limited supply because you'll need to do it for your test, your Unit 1 exam. But you just in general need to be able to do that in chemistry. So once you identify what's in limited supply, just like your ham was, then you can know how much bread you used, how much excess, that was the present excess that you used. Then you could know how much product you produced. Okay, you could know how much of the excess reactant was left. But the starting point was always finding the thing that's there in limited supply. Well, as you might imagine, to work these, usually they're not going to tell you how many molecules of each thing you have. They're probably going to tell you how many grams of each thing you have. So here we go. Let's say we have, I'm going to put it under the species of interest here. Let's say we have 72.0 grams, I'll put HAVE, have 72.0 grams of nitrogen. So I'll find my nitrogen, 72.0 grams of nitrogen. And what we have is 22.0 grams of hydrogen. That's my have. So here in a minute to work this problem, what you're going to see me do is I'm going to take 72.0 grams of nitrogen. I'm going to go to moles of nitrogen using the molar mass. For the 22.0 grams of hydrogen, I'm going to go to moles of hydrogen using its molar mass. And then I'm going to kind of do the whole what we need from the balanced equation, which is 1 to 3, and what we have from the moles that I calculated. So that's exactly what I'm going to do. And then we can answer these questions. So we'll be able to identify which one's in limited supply. Okay, the thing that is in excess, how much of that is going to be used up. And then a little quick subtraction problem will tell us, oh, well, I guess it's one more. No, the 2 is subtraction. So we're going to find out the mass of reactant that's excess reactant that's used, subtract it from what's there to get what's remaining. And the last step is how much NH3 is produced. But it's all going to start with identifying which one's in limited supply. So, do you guys have these molar masses? Yeah. Okay, good. There's a molar mass of everything. Can't go wrong. When in doubt, calculate a molar mass. Units of molar mass are grams per mole. So, like I said, my first step is to knock out the moles of the two reactants. So for nitrogen, I'm going to put 72.0 grams of nitrogen over 1. Molar mass is molar mass is 28.02, so 1 mole of N2 over 28.02 grams of N2. Round it to 3 sig figs, you're looking at 2.57 moles of N2. Again, the more organized you can say as you work the problem, the better off you're going to be. So I'll work an analogous problem to go from moles of hydrogen. I'll take 1 mole of H2 over 2.016 grams of H2, 3 sig figs, and you're looking at 10.9 moles of H2. So those are the two that you're going to see me make a have, as in HAVE, have ratio. You might be like, well, Mrs. Snipes, which one goes on top? Well, what I usually try to do is make them so that I have a number greater than 1. So you're going to see me put the 10.9 moles H2 over 2.57 moles of N2. All right, so here's my ratios. I'm starting with the need, though. Need. So the need comes from the stoichiometric ratio. Or stoichiometric coefficients that make ratio. And I like whole numbers, so I'm going to go with 3 moles of H2 over 1 mole of N2. You could have done it the reverse, but whatever species whatever ratio you go with, you have to do it both for the need and the have. So we would say then, of course, 3 divided by 1 is 3. So we have 3 moles of H2 for every 1 mole of N2. 3 moles of H2 per mole of N2. Sometimes I chant it to myself. What does it say? So that's what we need. That's our recipe. And I kind of explain where our have ratio comes from. From the previous slide, we came up with 10.9 moles of H2. That's what we have from that mass of H2, and 2.57 moles of N2. We divide it out, unless you're Rain Man, I can't do that one. 3 sig figs, you're looking at 4.24 moles of H2 per mole of N2. And then it focuses on what you have in the numerator, the species in the numerator. So can you see where I must have more H2 than I need? And sometimes and probably it says it right down here. Based upon the amount of N2, we have more, we have more H2 than we need. Have more H2 than we need. Have more H2. Oh, H2 must be in excess. Honestly, I'm not good at memorizing things, so So H2 is in excess. That makes N2 our special dye. N2 is in limited supply, and that's how we're going to answer the other 2 questions. Okay. Now, we're not going to reinvent the wheel, because here, to work the rest of the problems, you're going to see that we already had the moles of N2 and H2, and we're going to use that to our advantage. So, for instance, so H2 is in excess, N2 is in limited. Okay. So we need to use the limited supply reactant to find out how much of the excess reactant reacted. So we're gonna use that moles of N2 that we had before. Earlier in the slide, we came up with 2.57 moles of N2. We're like in the middle of a stoichiometric calculation. So what would the next term look like? And here's your hints down here. We have 1 mole of N2 reacting with 3 moles of H2. What ratio can go here to make moles of N2 cancel, leave us with moles of H2?
3 moles of H2 over 1 mole of N2.
Yep, 3 moles of H2 over 1 mole of N2. Perfect. how can we get from moles of H2 to grams of H2? Molar mass. And so it's going to be the unflipped version of molar mass. So 2.016 grams of H2 over 1 mole of H2. So what we've done is use the limited reactant, which was N2, to come up with the mass of excess supply. This is the mass used. Well, mass H2 reactant. All right, 3 sig figs. So you're looking at 15.5 grams H2 was used. So here's where, and I've seen it sometimes when I'm grading papers for your exam and such, you'll get to this point and you're like, well, I used more H2 than there was. That must mean that you misidentified the limited reactant. Do you see what I'm saying? Because here now, to get to how much was remaining, all we got to do is take how much we started with and subtract that from it. How much is remaining? We started with 22.0 grams. And from that, we subtract 15.5 grams. And we are, since we're subtracting, we round according to decimals. And you're looking at 6.5 grams of H2 will be left. That's like your bread. So that's kind of collectively what that looks like. So I can't overemphasize the importance of being able to identify the limited reactant, or the reactants there that's present in limited supply. So one last stoichiometric calculation. So we already know the moles of the limited reactant. Early on we came up with the 2.57 moles of N2. How are we going to get to moles of NH3 from moles of N2? Yep, 2 moles over 1 mole. 2 moles of NH3 over 1 mole of N2. And then how are we going to get from moles of NH3 to grams of NH3? It's molar mass. Which a few slides ago, we knocked out the molar mass of everything. A few slides ago, we came up with 17.03 grams of NH3 for 1 mole of NH3. You guys would tell me 3 sig figs. So you're looking at 87.5 grams of NH3 must be produced. And that was the last question. So it's like a little suite of questions. It's a classic. That can't be good. So the two ways that two other ways. So this is like the need and have ratios, comparing them. There's 2 other ways. One of these is to go ahead and if you have 2 reactants, pick one and see how much of the other you would need. And if you, and then make a conclusion from there. So if you, for instance, need 5 grams of that, but you have 10 grams of that, then this must be in excess. And what you started out was unlimited. If you do that calculation and you need 10 grams, but if you need 10 grams and you have 5 grams, that means that the other one was in limited supply. So you can deduce it from there. And then this one is kind of what we did with 3 quarts or with the handouts, where you can take your, and this one really, to me, what we did with the handouts was we had like 5 things that actually went to 5 reactants. To me, the best thing is to go ahead and see how much product each reactant could produce at that given amount. And then whichever one you get the least product, that's unlimited supply. So, so I've seen students do any of those 3. So there's actually 3 ways. So let's take a look, because it'll be kind of all kind of nice, neat little package. Let's take a look at the next part. You're like, I don't need a nice little neat package. The beauty of knocking this out is it's an associated part, and then that gives us a clean break. On Monday, we'll start with solution concentrations. But this is right up the alley of what you guys did yesterday in lab. Remember in lab, you for your CO2 in the first experiment, even the second experiment. The first experiment, though, I know you did this, that carpal tunnel, make out the CO2 go off. And so you actually calculated a mass of CO2 you drove off, or if you haven't, you will. But you also did a stoichiometric calculation of, based upon the starting mass of your sodium bicarbonate, how much CO2 should you get out, okay? That stoichiometric calculation, specific for starting mass of a reactant, going to find a product, is what we call the yield. Okay, so that's a yield calculation. All right. Oops. Drat. Theoretical yield. It's a yield calculation, theoretical yield. And it's funny because, like, when we study the scientific method, the term theory, people usually like, it's a theory. But a theory is a big, hairy deal in the scientific method of discovery. It's a hypothesis that's been elevated to a theory. But anyway, so theoretical yield. There's specific where you have, if this is my R, going to form P, okay? You're given this, and you're trying to find that. That's a yield calculation. So usually our yields are low, and I have 4 ideas here why your yields could be low. I'm going to walk you through each one, and I'll tell you, I shouldn't tell you, but these will be on your test in some form. I've asked them different ways, but I think it's important why you go in the lab and you don't get back what you should. Okay, so let's see, reaction, I'll just go through them one by one. So reaction kinetics. Now, if you stick with Gen Chem, the second semester of Gen Chem always includes reaction kinetics everywhere. So it's funny how chemistry instructors kind of get together, and that's how we do. The thing about reaction kinetics is just how fast a reaction occurs. I'm going to show you a graph here in a minute to try to convince you that we don't just, automatically occur, like the speed of light, which also doesn't automatically occur. It has a distinct amount of time that it takes light to travel from point A to point B. They aren't instantaneous. So, for instance, I know 30 seconds isn't a long time, but this is trying to try to describe to you where if we start out with reactants, red is reactants, okay, P is products, or green is products. So we see the concentration, we'll talk more about molarity, but the concentration of our reactant is going down, the concentration of our product is increasing. So what this says, if you find 7 seconds, so you're looking at, let's see, 6, 7, like here, find 7 seconds, go up like that, okay? At 7 seconds, which could seem like an eternity, you still have half of your reactants left, okay? So that's kind of what that looks like. So in other words, we just might not be patient enough for our reactants to proceed to form products. Another one, oh my gosh, and you're going to see a slide here in a minute, but we've been talking about, usually we say reactants goes to form products, and that's awesome. You read from left to right, we write chemical equations from left to right, but there are a whole lot of processes that actually, to a certain extent, the products go back to form reactants. So if that's the case, you're never going to get 100% products, because they're always going back and forth to form reactants, reaction from product, product from reactants. That's what we call chemical equilibrium. And if you've probably been introduced, and this is also a Gen Chem 2 topic, of this whole acidity, basicity, pH, that is one major chemical equilibrium. So this is an example here between molecular hydrogen, molecular iodine to form a hydrogen iodide over here. Notice in this case, this is actually time. Kind of think of time along the x-axis. Okay, so we start out with no product. It's all, and then along the y-axis is concentration. So we have H2I2 and none of this, none of the product. Given a certain amount of time, notice that we kind of, I'm not sure where it would happen, but somewhere maybe around here-ish, things level out. And this is what I was saying, given enough time, things are going to settle down into a constant concentration of your product, your HI, and you still have some of your reactants left, H2 and I2. Okay, that's the equilibrium part. That's pretty fun. Another one, and I think we ran into this even with your magnesium. In the background of your magnesium reacting with oxygen is an unwanted side reaction between magnesium and nitrogen, because of course this room's got mostly nitrogen, like 80-20, nitrogen, oxygen. So that's an unwanted side reaction. So in other words, some of your magnesium oxide was really magnesium nitride. It happens, and there was a way we could try to clean it up, but we didn't have patients do that. So it's kind of like you can't help it. Some of these things are what we say inherent to the experiment. The last one is physical losses. Now I have a slide here coming up to explain what gross errors are. And gross errors are, I call them oops errors. Okay, oops. Now physical losses are not oops errors. They, again, I'll use the word inherent, are inherent into your experiment. Here's what I would say about physical losses, especially in pharmaceuticals. You figure pharmaceuticals have to be pure, 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 pure. And with purification steps, generally you're going to lose some product. There are, like if you take organic chemistry, they will tell you some of your, some experiments, you're doing good to get 56% yield or something like that, 50% yield. That's just the way it goes. And a lot of product oftentimes is lost during purification steps. Okay, so when you guys do a stoichiometric calculation where you start with a mass of reactant, you get to a mass of product. That is a yield. That's a yield calculation. So you could get that if all the things I described earlier fell into place. So if all of the limited supply reactant proceeded to form product, if there weren't any competing reactions, there's a lot of ifs, okay? And if you were to be able, for each step, if there's multiple steps in your chemical reaction, to recover your product, okay? That's a lot of ifs. So that, my friends, is why you usually get less than you thought you were supposed to get. Gross error, that's my oops error. So they would include the oops, sounds like oops, you spill something. Okay, you write something down wrong. You don't have your lab partner like double checking your masses. Okay, you screw up in your calculations. Oops. So these are avoidable. So the gross errors are avoidable. The physical losses are just kind of inherent to the experiment. So you see the word ineptness. So I don't mean to give anybody a hard time, but gross errors are due to the ineptness of the investigator. That would be us or you or whoever did the experiment. So let's see what sort of calculation we could have associated with percent yields. Now, you guys actually, for handing in your sodium bicarbonate, are going to come up with a percent error. I was thinking about this yesterday when I was doing pre-lab, and today I'm like, you know, it just seems like you could have done an easier calculation. But for percent error, you guys are taking your theoretical minus your actual, like theoretical. But anyway, so this one is a little easier. So this is not percent error, this is percent yield. So you take the actual, what you got experimentally, and divide it by what you thought you should have gotten. So in other words, so this is what you got. And this is from stoichiometric calculation. So let's do, and they're pretty straightforward. Let's do an example of what that would look like. Now I know this example looks like, you're like, oh, it looks like how can we get that done in 5 minutes? Well, actually, the first part kind of reminds you of what we did looking at this reaction before. We said before that if we have 1.25 grams of sufficient, now we know that sufficient means at least enough. It might be right at the amount or a little bit in excess. So sufficient. We said before we did a stoichiometric calculation, and that's my yield. We said, or my theoretical yield, 1.62 grams. That is my theoretical yield. Theoretical yield. So you guys went and you ran the experiment, and instead of 1.62, it's generally low, although I say that in I think the experiment you guys are doing next week is what we call the copper lab, and your yields will be higher than 100%. But yeah, you got back less than 1.62, so instead you got 1.08 grams, and that's my actual yield. That's what you got. I can never spell yield, but I think that's okay. All right, so don't make it harder than it is. So all we're going to do is do a ratio. We're going to take our percent yield is going to be our actual yield, 1.08 grams, divided by theoretical yield, 1.61 grams. And to get it in parts per 100, we're going to multiply by 100%. Oops, I'm missing that. Times 100%. 3 sig figs, so it's 67.1% yield, which, like I said, when you're given information about experiment, they will tell you what your expected yield is. You know, scale this up from the lab to a factory, right? So, all right. So both of those parts will be due when we meet again on Monday. It will be October? Will it be October? Yeah, all right.